Hi, gang, Math 6610, transitioning into something we call MANOVA, which I think of like just multiple Anovas. Uh, but the quote-unquote technical name would be multivariate analysis of variance. And I think learning some, if we just started with MANOVA, it could be a very, very, very challenging statistical technique. But I hope that we built the foundation with the Anova principles to where learning MANOVA, which is slightly more complicated, is an easy transition. Now let's just review very, very quickly what's ANOVA. Well, we have a dependent variable y, which is quantitative, and an independent variable x with more than 2 levels. Now, as we move into more sophisticated techniques in the ANOVA family, we can often run these with the independent variable x having 2 levels, because if we would get into like a maybe a two-way ANOVA, then it would make sense to conduct on an independent variable just 2 levels. Okay, so an example of just a standard ANOVA would be, say we have a final exam score, obviously given a common final exam across Professor A, Professor B, and Professor C. So let's just assume this is a statistics class. We have 3 professors teaching the class. We want to see if there's any difference in the mean final exam scores across professor. Now we can modify this a little bit, just a little bit of review here. If we wanted to add in a covariate, maybe a pretest score in ACT, we could do that. Now, let's move into the MANOVA design. So let's assume that we wanted to dive into this problem more and not just examine the overall final exam score, but let's say we wanted to break the final exam score down into 3 sets of questions. The questions that were geared toward testing descriptive statistics, how do you calculate a mean? How do you calculate a median? What's a box plot? Things like that. Other questions on probability, probably normal distribution, sampling distribution, central limit theorem, and then another set of questions on questions on inference. Get into estimation, confidence intervals, margin of error, hypothesis testing, things like that. So let's just say, to make this a little clear, let's say the final exam had 25 questions. And let's say these were questions 1 through 8, and these were questions 9 through whatever, 18, and these were questions 19 through question 25. So we would get a score on these, a score on these, and a score on these. So this would become respectively our Y1, Y2, and Y3. So that's what MANOVA allows us to do. It allows us to look at the differences in Y1, Y2, Y3 simultaneously, in this case over Professor A, Professor B, and Professor C. Now, I think the obvious first question is, well, okay, let me pump the brakes a little bit. Thinking ahead just a little bit, what would a Mankova design look like? It seems a little fuzzy, doesn't it? Let's see if we can clear that up just a little bit. Okay, so what would a Mankova design look like? Well, it would have multiple dependent variables, Y1, Y2, Y3, Y4, whatever. An independent variable, which is categorical. That's the ANOVA part of the Mankova. And then we would add in a covariate, as we've seen previously. So, again, in your bag of tools, you would be prepared to handle something like this based on your study of ANOVA, Mankova, and now MANOVA. All right, so why not conduct multiple ANOVAs? That's what a lot of people want to do, and that's just the incorrect way to approach a problem like this. First of all, it would inflate the family-wise type 1 error rate. Not cool. Secondly, I've seen this happen. You get into a situation where the individual ANOVAs may be significant, but in combination they may not be. Or I've also seen that none of the individual ANOVAs are significant, and in combination they are. So sometimes it doesn't turn out the way that we would expect. Another thing, MANOVA techniques control for the dependency between the multiple dependent variables. In other words, if we have high correlations, which we often do, you would think in this example back here, looking at a score on descriptive stats, probability, and inference, you would probably think that these things would be pretty highly correlated, because you would think that the students who score higher on the final exam would probably score higher on each of the pairwise components. In other words, if a student scores higher on probability, I would assume they probably score higher on inference. Not always. We know how learning can take some wacky turns from time to time. All right, 3 assumptions that I want you to put on your radar. I'm going to run through a quick MANOVA at the end of this video. Again, just something very quick, just to kind of get to wet the whistle, if you will. My grandmother used to say that. But I'm going to show you how to test the assumptions in another video. So again, have on your radar, the assumptions are multivariate normality. Now let's pump the brakes on that and dive in a little more. Univariate normality, which we have done previously with Shapiro, would dive into the dependent variable y1 and test to see if this sample data appeared to come from a distribution that is normal. Then we could do it again for y2, do another one for y3, y4, up to however many y's that we have. That's fine and dandy. Those are things that we care about in MANOVA. And in a univariate setting, it's things we care about as well. But in the multivariate normality, we not only want to be able to test the individual dependent variables come from a normal distribution, this multivariate normality goes a step further. It also tests to see if any of the linear combinations of the dependent variables is normally distributed. So when we conduct a MANOVA, we want to examine the univariate normality, but the main thing we have on our radar using Wilkes Test is the multivariate normality. Next thing we want to get into is we want to get into homogeneity of covariance matrices using Wilkes Test. In the univariate world, in the Anova world, we want to test that the variances are equal across the K groups. In the MANOVA world, we also want equal variances for each Y. We also want the pairwise correlations to be the same, and we want to dive into the structure of the variance-covariance matrix to examine the homogeneity assumption. Now, if you've taken my 5500 class, you know we got into a lot of variance-covariance structures, right? You get into it with our betas. We got into it with our error structure, the residual structure. We got into it in a lot of situations. So it's bouncing kind of off of that idea. And as always, except repeated measures, dependent samples, t-test, we need independence. All right, let's throw some data at you. So let's say that we have so our dependent variable. We have 2 dependent variables, y1 and y2, and we have 1 independent variable k, which has 3 levels: k1, k2, k3. Well, it just so happens that I have put that information into R. And in Blackboard, you will have the data set. It's just called MANOVA. I'm not feeling very creative just yet. So I just want to run through how we would run a MANOVA. You're going to see it's very, very, very simple to do. And how we can test an effect size. So the first thing we need to do is to mash the y1s, the dependent variables, together. And to do that, we use what's called the cbind function in R. All right, so we're mashing those suckers together. Now, the next thing we do is we just run our model, and there's a nice command built into the base R package called MANOVA. And we want our dependent variable across. And again, it has to be the dependent variable where we mash these things together. We binded them together. I don't know why I say mash, but it's just what it is. All right, so as you would imagine, as we have become accustomed to do, run our model, go to the summary of the model, and you can see that we get, as a default, what's called p-lice trace. So p-lice trace, the value, this is not the test statistic, this is p-lice trace, is 1.35 on degrees of freedom 2,9. The test statistic is under approximate F. The numerator, denominator degrees of freedom are 4,18. And our p-value is statistically significant at the 0.01 level. Now, turns out there are 3 other tests that are commonly reported, and let me show those to you. The other one, well, let me just go back up and get, just add to this. The other one that is often, sorry, I can't type and speak, reported is the Wilkes Test. Now, the Wilkes Test is a little bit more aggressive. It usually ends up with a smaller p-value, but it didn't. And yeah, it did. Yeah, okay. Yeah, it typically has more power. It has a higher F statistic, hence a lower p-value. So we can think of Wilkes having more power. It's a more aggressive test. If you want a more conservative test, which will yield the I forget what it is. Lawley, I believe. Yeah. This one typically gives us the highest p-value. Well, in this case, yeah, 0.92. Yeah, okay. I thought I was losing my mind there. And what it does, you can notice that the difference turns out to be the F statistic, and then on the degrees of freedom, which is calculated differently for each of these tests, obviously yielding a lower p-value. So at this point, I kind of want you to just get in a habit of, unless told otherwise, instructed otherwise, to run p-lice trace. It seems to be well, it is the default. It seems to be the one that I see reported the most. Now, something that would be kind of cool to follow up with is effect size. And it turns out that effect size in R for MANOVA is very easy to find. We just need to install the package or access the library for effect size, and then we run effect size at a squared would be appropriate for this, and let's just run it over our model. Okay, why is it not working? Huh. Oh. Yeah. For some reason, that always gets me. For some reason, and I'm actually kind of glad that happened, so it'll get your attention. For some reason, we have to put 2 colons there. Okay, anyway, the partial eta squared turns out to be 0.68 with the confidence interval provided there. So we end up with a high effect size. Now, something we can do if we want to examine the individual ANOVAs, and again, we don't want to do that, but if we did want to examine the individual ANOVAs, we could just run the summary AOV command for the original model, right? And what this will do, it'll run 2 independent ANOVAs. In other words, it'll run an ANOVA on Y1, not considering Y2, and Y2, not considering Y1. Same thing if we did just a standard ANOVA of just Y1 over group. Well, I don't even need that, right? Let's trying to save time, and it's just not working. All right, so if we ran a model 1 just of a straightforward ANOVA, a one-way ANOVA of Y1 over the group, notice that we get the same F statistic and the same p-value, and it should be no surprise to you if we ran another model, model 2 over Y2 independent of Y1, this is what we get. So anyway, what I want to show you is this command right here gives us the individual ANOVAs not residing in the MANOVA family. Now let's shoot back over here. What I did is, if I was going to, well, actually I wrote some things out. I'm not really sure why I did that. But what I want you to focus on is the bottom part. So what I say here is, I say p-lice trace test is statistically significant. So p-lice trace is 1.35, F 2,9, 9.42. Again, that comes from this information. All right. So we're statistically significant at the 0.001 level. So we say that the results indicate that I got on tunnel vision here and used X instead of K. So anyway, the K group has a statistically significant association with both Y1 and Y2. The observed effect size of group on Y1 and Y2, again, comes from the bottom. Well, where is that? Comes from this output right here. And I just say that we observed a large effect. All right, gang, that's all I got for this video. Take care.